Okay, the next lecture today, all right? Okay, at the end of the previous lecture, we have this representation for our transfer function. Okay, the first part is the definition of transfer function, which is defined as the ratio between the Laplace transform of the output to the Laplace transform of the input. Okay, this is the definition of the transfer function. But how do you determine what transfer function really is? It comes from here. Why? Because once you know the differential equation, you know what Q is, you know what P is, and then you can determine the transfer function. Okay, these are knowns. P of x and Q of x are all polynomials of S. Okay, another important thing is that based on the definition of transfer function, we have equation 6. Equation 6 is a very wonderful result. Why? Because it tells you the output is actually the product of the transfer function and the input. With one simple equality, it tells you how input interact with the output. Remember that what is the very purpose of control? The very purpose of control is that somehow I need to find a way to manage, to manipulate my input so the output of the system can conform to my requirements, right? Manipulate input to get the output I want. But that mapping the relationship between input, how do I change input to get the output that I want, is not that easy, because traditionally I need to solve the differential equations to figure out how F impact Y. And it is, I wouldn't say tedious, but it is a process. And the interaction from F to Y somehow, I wouldn't say lost, but somehow is not that clear through the process. However, after the application of Laplace transform in the X domain, the interaction between Y and F, how F changed Y, become much, much more clear, because it only involves one simple mathematical operation, which is multiplication. You multiply the input with the transfer function, and then you get the output, right? I wouldn't say this is the simplest equality in the world, but it is as simple as can get. Okay, so this is indeed a great result. And this also explains why we want to use Laplace transform, which itself is a complex mathematical process. All right, but by using Laplace transform, we can come out with such a simple result, which can help us relate input to the output in a very direct format. And that is exactly what I said, what we want. Okay, again, engineers prefer simplicity, not complexity. All right. Now remember that in getting this particular result, equation 5 and equation 6, we have made some assumptions. We assume all the initial values associated with Y, with input and outputs, are zeros. All of them are zeros. Of course, these are not always true. Actually, sometimes they are not true. But generally speaking, most of the time, they are not true. So if the initial values are not all zeros, then after you can demonstrate that what I will get, the equation 5 will turn into this equation, okay? This part remain identical, okay? But this part, z of x, represents the effects of non-zero initial conditions, okay? It's a messy process, but all in all, z of x represents the overall contributions from all the non-zero initial values, okay? And if this is the case, let's divide this equation by Q of x, and this is what I will get. Here, we should have a P of x ahead of fx, all right? So y of x is actually the sum of Q of x divided by P of x, and the product of P of x and fx divided by Q of x. For this part, we call it zero input response. For this part, we call it zero step response. This part, so this represents the total output. And from this equality, it tells us the total output actually consists of two parts. One, from the initial conditions, because z of x is the result of summarize all the impacts from the non-zero initial values. And fx, this part come only from the input, which is f, all right? Now, let's go back to Laplace transform and summarize what it can do for us. Laplace transform in control series convert time domain functions into complex frequency domain representation. So x is actually a variable of complex frequency. Simplify the analysis of linear time invariant system. It transforms differential equation into algebraic equation. Okay, this is an algebraic equation, right? You don't see any derivative here. You just don't see any differentiation operation here. It transforms this differential equation into this algebraic equation. All right. So making it easier to analyze system dynamics, stability, and response characteristics, we will study all these properties in the later part of this course, while also enabling the use of transfer function for system modeling, which means here, G of x transfer function, it represents a mathematical model of the system. What system? This system. Transfer function is actually the mathematical model of the system. In time domain, the mathematical model of the system is differential equation. In X domain, transfer function is the mathematical model. All right? Because only when it can fully represent the dynamics of the system can we have this result. Okay? Only when G of x can capture every piece of information of the system can I have this result, because you times G of x, you tie fx, which is the Laplace transform, the input, which is the transfer function, you can get the output. Okay, and therefore, if this is the true output, G of x must cover every aspect of the system. If that's the case, G of x, which is transfer function, represents the mathematical model of the system in the X domain. Okay, so let's talk more about transfer function. Okay, again, let's go back to our differential equations. Here, if the initial conditions are all zeros, the transfer function is G of x, all right? And with G of x, I have y of x equal to G of x times R of x. I'm sorry that sometimes here, the input is f, okay? Here, Now, in here, the input is R. I'm sorry for the inconsistency of the samples. Okay, I'm sorry for the inconsistencies of the samples that are used, of the notations that are used. I'm apologize for that. Okay. Okay. Now, again, P of x and Q of x can be easily determined from the given differential equations. And this is the transfer functions. If initial conditions are not all zeros, then y of x can be rewritten as this. This is the same as this, okay? And so mx represent the contribution from the initial conditions, all right? So this part is what we call zero input response. What is it zero input response? Because when input is zero, this is zero, and the total response will reduce to only this term. So the zero input response represents system with no external input, which means no external input because R is zero. So the right-hand side of the equation is zero. Therefore, this term is zero. Therefore, y of x is equal to mx divided by q of x, driven solely by initial conditions. This part is not described by the transfer function, okay? Transfer function has nothing to do with this part. Transfer function is given here, all right? So transfer function only related to zero state response, which is this part, okay? It represents system response with zero initial conditions. If initial conditions are all zeros, then mx is zero. So total response only consists of zero state response. The term zero state means represents zero initial states or zero initial conditions. Represent the system reaction to external stimulus, okay? Depends on both system characteristic and the input, right? This represents system characteristics. This represents input, right? So those that respond depends on both system characteristics and input. The transfer function describes this part, okay? Transfer function is responsible for zero state inputs, and transfer function at the same time only explains the zero state response part of the output. Okay, remember output is made of two parts, zero input response and zero state response. Okay, so because what we are dealing with is linear system, so the principle of superpositions is applicable. Therefore, the total response is the sum of zero input response and zero state response. Okay. Now let's just skip this PowerPoint slide first for the time being, because we'll go back to this representation later. Okay. Remember that now. Remember that we define zero state response as this. Okay, where P of x over Q of x is the transfer function, and here, please remember that Q of x is what we call characteristic equation. Okay, this term characteristic equation, you should have seen it before in the class of engineering mathematics when solving differential equations. Okay, you should have encountered characteristic equation. Okay, if you have no collection, you just don't remember it. Okay, doesn't matter. I will review that idea later in the later part of this course. Okay, now the roots of the characteristic equation is what we call poles. In the course of engineering mathematics, the roots of characteristic equation is called eigenvalues. Same thing, different terms. Okay. Okay. Q of x is a polynomial, therefore it has roots, and its roots are called poles. Similarly, P of x, this is P of x, is also a polynomial. Okay. So, and the roots of P of x are called the zeros of the system. All right. Let me emphasize again, the transfer function does not take initial conditions into account. All right. Initial conditions appear here. Okay. So transfer function has nothing to do with the initial conditions. Okay. Now, more remarks about transfer function because of its importance. A transfer function is a mathematical model that relates output of linear time invariant system to its input. How? G of x, okay, y of x is equal to g of x over f of x. All right? That's how they relate them, how transfer function relate the input and output. Okay? It is typically expressed in the Laplace domain where the time variable is replaced by the complex variable, x. So x is what we call complex frequency. Mathematically, it is always a complex variable, all right? Ratio output to input is in the Laplace transform, okay? So transfer function is the ratio of the output to input, but only in the x domain, okay? Now, transfer function reveals stability, steady state behavior, and dynamic response, okay? Because every aspect of the performance of the property of the system are embedded in the transfer function, okay? So naturally, studying transfer function become a very important topic in the course of control, okay? Transfer functions are a fundamental tools for analyzing and designing control systems, providing insight into system behavior without solving complex differential equations. I love that. Without solving complex differential equations. I'm sorry, this is zeros, this is poles, okay? With the specifications of pole and zeros, transfer function can be rewritten into this form, where here z1, z2, zm are roots of the numerator polynomial and hence zeros of the transfer function. Similarly, P1, P2, all the way up to Pn are roots of the denominator polynomial, hence they are the poles of the transfer function, or they are the poles of the transfer function. Why do we have to identify what are the poles, what are the zeros? Because they are important parameters of the transfer function. Because as you will see in the near future, the locations of these zeros of poles matter a lot. Okay, we care about where zeros and poles are located. Okay, the distance between zero or pole to the real axis and to the imaginary axis and to the real axis matters a lot. Okay, all right. So understanding the system. In control system, the main focus is on shaping the total system output, but properly manipulating the system input. That is the basic goal of control system. Since the initial condition cannot altered by the external input, all right? Input cannot do anything with initial conditions because initial conditions are pre-existing conditions, all right? So we cannot do anything about it. Let's say you want to control a car, okay? What you can do is you can press the pedal to accelerate or hit the brake to decelerate the car. But the velocity of a car depends on two factors. The first factor is, of course, how you operate the car. But the second factor is right before you take control of the car, what is the location? What is the velocity? What is the speed of the car? Okay? And that is the pre-existing conditions. Where the car is, how fast it ran. These are pre-existing conditions. before you take over, they already exist. So what you do next will have no impact on those existing conditions. But you still can do something about the car, okay, by driving the car properly, okay? It's just that for those pre-existing conditions, for those initial conditions, for those response caused by initial conditions, there is nothing you can do about it. You just accept them as the way they are, okay? But there are still room for our effort. That is, let's take care of the output by managing or by manipulating the input properly, okay? So control system design primarily concentrate on developing control law and regulates the zero-state response, okay? Now, what about the zero input response? By properly designing the control input, the desired total response can be achieved while the inference of the zero input response due to initial condition naturally decay in stable system. I have to assume the system is stable. We will talk about the definition of stability later, okay? But if I assume the system is stable, then the impacts or the inference or the zero input response will naturally decay over time. It will naturally go away, all right? Okay. All right, so, this is a very important concept. We concentrate on developing control law that regulates the zero-state response. And that implies that transfer function really matters, okay? Because if you know the transfer function, you know the zero-state response, provided that the input has been given, all right? Now, the transfer function is a fundamental mathematical model for analyzing and designing a TI system, as it describes the input-output relationship in the frequency domain under zero initial condition, okay? Actually, this statement is something I have mentioned before. I just want to rephrase the concepts again so that hopefully it can impress you more, okay? Because this concept is fundamentally important, okay? Now, there are some parameters of transfer functions we hear about a lot, including order, Hall, and zeros, okay? And we all know what they are, and we will study their impacts in the future. Now, let's study the transfer function, okay? Now, to do that, let's first look at the total response. Now, the total response, as we just described, actually consists of two parts. The first part is what we call zero input response. And the second part is what we call zero state response. And their input response are made of modes, are made of modes. Now, what is a mode? A mode refers to the distinct dynamic behavior exhibited by the system. And that system, for nth order system, it actually possess n different types of distinct dynamic patterns of n different types of distinct dynamic behaviors. And the zero input response is the linear combination of those n distinct dynamic behavior, okay? It seems very abstract. So let me give you real world examples. So let's first clarify the relationship between zero input response and modes. As I just described, these are modes. These are modes, okay? And their input response are actually the linear combination of all the modes, okay? Okay, let's say we are considering an nth order linear time invariant system. And here we only consider zero input response. If this is the case, remember that for nth order linear time invariant system, it can be described by this equality, right? Now, assuming I have zero input, therefore ft is zero. So the right-hand side of this equality becomes zero. So the differential equation now look like this. Now, the subscript here, I insert a subscript under y here to denote that here, what we are considering is zero input response, okay, not total response, because here input is zero. Now, Q of D is actually this, right? That's the definition of Q of D, okay? Now, the next thing what we want to do is I want to solve a differential equation, okay? The first step for doing that is I assume the zero input response can be represented as the product of C and e to lambda t, okay? This is a very important assumption, okay? How do you know this assumption is right? I don't know that in the beginning, but I will justify that by plugging it into this differential equation. If this assumption is right, is not violated, then I can find a way to find the right set of lambda such that the right-hand side of this equality will always be equal to the left-hand side of this equality will also always be equal to the left-hand side of this equality. Okay, let's just do that. Just plug this into my differential equations. Okay, to do that, we need to take the first derivative, take the derivative of y0. Okay, easy, because we know y of t here is c times e to lambda t, and it's the first derivative is this. The second derivative is all the way up to here. All right, can you see the similarity between the derivatives and this exponential function? Okay, here d, here lambda, here not d squared, double derivatives, I have lambda squared. Here, nth the derivative, I have lambda to n, right? Or lambda to exponent n, right? Okay, can you see? Please pay attention to such a similarity, okay? Now, if this is the case, I will just plug these results into these equations, okay? And these results, they have two common terms. One is, of course, C, and the other is, of course, e to lambda t. So I just take them out, okay? So this is what I get, okay? Now, for this equality to be true, there are three possibilities. First, C is zero, okay? But C is zero is really not a choice, because if C is zero, then y of t is zero. This is what we call trivial solution. It satisfies the equation, but it does not mean anything. Okay, so it's pretty much useless. All right, let me take a quick break. I really need some water. Hopefully, taking the class of control in English is not a frustrating process for you, because control itself is complex. English itself is also challenging. When you mix those two things together, it can be more challenging, more undesirable, because as I said, we engineers prefer simplicity rather than complexity. But let me assure you, personally, I'm doing the best I can to bring up positive energy to this class, okay? Because in the bottom of my heart, I think learning in English, no matter how difficult it is, it will pay off in the future. It will pay off in the future. And that I can assure you, okay? Nowadays, sometimes when I listen, when I'm driving a car, I can now watch YouTube, but I can listen to YouTube, right? Even the speakers, even the programs are given those persons speaking English, I think most of the time I can understand. Okay, I know what they are talking about. I don't need to read the subtitles. Okay, and I'm not saying I'm a very good English speaker or listener, but I can understand what they are trying to say, what they want to, what a message they want to the idea, what ideas they want to convey, what message they want to give me, and I consider that I would being able to receive those messages. I consider that a great privilege. Okay, especially those messages are given in English, because there are so many great people in this world. They speak in English, not Chinese, not Taiwanese, not Mandarin, but it's English. Okay, if I can understand what they said in their mother tongue, I consider it a great privilege, because no matter how good AI is, something will lost in the process of translation, because English and Mandarin, they are just two different animals. They are not identical. Not every concept in English can be perfectly converted into Mandarin. This is also true the other way around. Okay, if you listen to sounds written in Mandarin and listen sounds written in Taiwanese, they are not the same things. Okay, a sound written in Taiwanese can touch you deeply in the heart due to its Taiwanese cultural background. But if you translate the lyrics into Mandarin and sing it again, it's totally different. The flavors wouldn't be the same, right? Because every language has its own cultural background, its own way of thinking. And English, as I all understand, is a universal language. So learning English, no matter how frustrating, how difficult the process is, I think it will pay off, especially in the long run. And think of it, okay? You are only in your 20s, early 20s, right? And people already say that in the 21st century, half of you will live longer than 100 years old. And I think that is very, very true. And that is very likely to happen. Okay? If you know how to take care of your body, okay, don't waste, don't wait, over waste your energy, okay, on work, on making money, on whatever. Okay. I think it is very likely, I'm pretty certain all of you have a very good chance to live longer than 100 years old. So if you learn your English in your early 20s, even through hard work, even through a frustrating process, that benefit will last. You can use that skill for another almost 80 years, right? Okay, for another 80 years, I can enjoy the benefit of speaking good English. Okay, that I think is really something we can all, no, not me, you can looking forward to. Okay, all right, let's go back to our lecture. Okay, control system. All right, now what we have here is C can be 0, but it will give us trivial solution, which is useless. And can this be 0? Of course not, because exponential function look this or this, right? Depends on lambda is negative or positive. So it is not 0. So the only possibility, the only hope that this equation can be satisfied is that this polynomial is 0. Now, so the next thing we need to do is to find out what the roots are for this polynomial. What is the name for this polynomial? Of course, it is called the characteristic equation. Okay, last time when we say characteristic equation, we were referring to Q of D equal to 0, right? Okay, here it is Q of lambda equal to 0. Different independent variable, but mathematically same thing because they have the same identical representations, which is this polynomial. Okay, it's just that the variable has different physical meanings, but mathematically they are identical. They are the same thing. So this is the characteristic equation you encountered in the course of engineering mathematics. And Q of D equal to 0 is the characteristic equation used in the course of control. Mathematically, as I said it, this is probably the third time. They are identical, okay? So let's assume that now what do we call the roots of the characteristic equation? We call it poles, right? The roots of the numerator of the transfer function, which is the root of P of x, are called the zeros. The root of the characteristic equation, that of the root of Q of x or Q of lambda, same thing, are called the poles. Here we assume all the poles are real. Okay, if this is the case, Q of lambda can be rewritten or it's represented as this, where lambda 1, lambda 2, lambda n are distinct. Here we assume lambda 1, lambda 2, lambda n are distinct real numbers. When I say distinct, means their values are not the same. Okay, if this is the case, their input response can be rewritten as this. All right. Okay. Here, remember that this is the characteristic equation. Okay. Q of lambda or Q of D is the characteristic equation. Okay. Now, each of the explanation function here are the modes of the system. All right. And here it just shows the location of one pose. Okay. Let's just skip this slide for the time being. All right. So that's one type of modes. And that type of modes occurred when I have real poles. Okay. But poles are not necessarily always zero and always distinct. I can have repeated poles. Let's say if this is the case of my dynamic system, then as you have learned before in the course of engineering mathematics, their input response or the solution of this differential equation, which in the course of engineering mathematics is a homogeneous differential equation, and this is homogeneous solutions. Okay, so now in this case, the root lambda repeats twice. So what we have here is repeated roots. Let's say it repeated more than 2 times. It repeated r times, like this. Then in the course of engineering mathematics, we all know that in this case, the solution to this ordinary differential equation should look like this. Let's say now the thing are a little bit more complex. We have repeated real roots. We have also distinct real roots. Doesn't matter. Eventually, because this is a linear system, superposition applies. Therefore, the final solution to this problem is this. Okay. Again, every single terms appear on the right-hand side of this equality represent a mode of the system. Okay. And the mode of the system, therefore, I hope this statement starts to make sense to you. A mode refers to a distinct dynamic behavior. A distinct dynamic behavior. Why are they distinct? Because if the value of lambda is different, it is different, okay? And the overall zero input response is actually the combination of that n distinct dynamic behaviors. So how do I understand the input response? I understand the input response by first taking the input response apart, one mode at a time, right? That is how we understand a machine. How do I understand a machine? How it works? How a machine works? Okay, we take it apart, component by components, and identify the functionality of every component. And then we know how those components interact, okay? That is the process of engineering analysis. We just take things apart, study every component, study every element. By understanding every component, every element, we know when we put those components together as a system, we know how it operates, right? Same thing happened here. When we want to understand the input response, we look at its modes, okay? And now, there is a certain possibility. The first possibility is distinct real roots. The second possibility, when it comes to eigenvalues of poles, is repeat the real roots. The third possibility is I have complex conjugate roots. Okay, that is lambda now is alpha minus plus j beta. Okay, when it comes to complex numbers, it always comes in pairs. That is when you have alpha plus j beta, alpha minus j beta will appear at the same time. This is always the case. There is no exception, okay? Maybe in the area of quantum mechanics, there is exception, okay? But I really don't understand quantum mechanics. So at least in the classical physics or the physics that we understand so far, complex numbers always come in pairs, right? Now, here, remember that we assume y0 of t is equal to E lambda t. Now, lambda is alpha plus j beta, and lambda is alpha minus j beta, all right? So, this is our zero input, the resulting zero input response, okay? At the first glance, it really doesn't make a lot of sense. Why? Because y of t, what is y0 t? Is the output of a system. The output of any real physical system in the world is a real number, a function of real number, okay? When it comes to temperature, when it comes to displacement, when it comes to velocity, acceleration, voltage, current, whatever physical variable, they only have real parts, right? None of those physical variables have imaginary part, right? So in that sense, complex numbers really do not exist in the real physical world, right? Now, so y0 of t, which is the zero input response of a real physical system, has to be a real number function, all right? But here, if you look at the right-hand side of this equality, you see complex variables. I don't know what C1, C2 are. I don't know what alpha, beta. But one thing I do know, real number cannot equal to complex number. The only possibility that these two are equal is that a complex number is no longer a complex number because its imaginary part now becomes zero. That's the only alternative, okay? There is no exception, okay? So at the first glance, that this equality doesn't make sense. Doesn't make sense because real number does not equal to complex number. The trick here is I assume C1, C2, again, to be a complex conjugate. All right? If this is the case, let me just plug C1 into here and plug C2 into, C2 into here. And this is what I will get. About arranging, by rearranging these terms, okay, this is what we will get. Okay, I'll skip the mathematical process because it's really not that tedious. Okay, all right. So now everything makes sense because in the end, here what we have is a real value function. Okay, now the important thing here again is the role of alpha and beta. Remember now, here lambda is equal to alpha minus plus j beta. Okay, so we saw this more than once. Okay, alpha appear here, so it determines the shape of the envelope of this response. And beta, which is the imaginary part of lambda, determines the degree of acceleration or the speed of acceleration. Okay, remember we saw that before, right? Last time we saw it, we saw this PowerPoint slide, and the complex variable is the lambda, the x, which is what we call complex frequency. Okay, and we saw this image before. Okay, this is the envelope determined by, in this case, E sigma t. All right, so which is the real part of the complex frequency, and the acceleration. The frequency of the acceleration is determined by omega. Well, omega is the imaginary part, and remember, omega represent or correlate with what? Frequency, because it governs the speed of the acceleration. So the complex frequency x equals to sigma plus j omega, generalized frequency to capture both acceleration and exponential growth and decay. All right, frequency itself, okay, complex. That means complex frequency go one step further than frequency. Okay, it captures not only acceleration but also exponential growth. Okay, that is the envelope. That is this part, or here, this part. Okay, so real numbers correlate or relate to the overall growth, exponential growth or exponential decays, determines on sigma is positive or negative. And the imaginary part, which is omega, captures the acceleration. In control system analysis, it is the central concept behind the Laplace transform and analysis. Okay, this central concept of complex frequencies. All right. Now let's, okay, time is almost 12 o'clock. Okay, okay, let's call it.